Yeah, so thanks again for coming down. We're still coming in and finding our seats, but really excited to be able to give the floor over to Florian with APTIV. Florian is one of COVESA's newest board members, just recently added for this next cycle, and very excited about having APTIV. Actually excited to have the APTIV Wind River acquisition over so that we can get on with the program and start working on some engagement there. But we're really pleased to have Florian. Florian is the Senior Director of Middleware and DevOps at APTIV, and so without further ado, we'll go ahead.
Thank you very much, Steve. Nice to meet you, everybody. My name is Florian. Thanks for the introduction, Steve, and I'm part of APTIV's CTO office responsible for our middleware and DevOps strategy. I'm based in Germany, south of Germany at the beautiful Lake of Constance. And yeah, a lot of people from APTIV traveled today or yesterday to Portugal. We have almost more APTIV folks in this room than others. No, it's a joke. So we have 4 or 5 people here in the room. And today we are talking about sustainable software architecture development for future vehicles. Feel free to interrupt me anytime. I like an interactive presentation. So raise your hand and tell me your question. I will stop from slide to slide and also ask you if there are any questions. And yeah, that's it. So let's kick it off. During the next 20 to 25 minutes, we are talking about the vehicle architecture evolution as well as our vision of the software-defined vehicle ecosystem. The first part of the presentation is more focused on in-vehicle topics, and the second part of the presentation is more focused on cloud topics. So DevOps and our vision of the next generation architecture and tools that we are using to develop automotive products. Tools such as unit testing tools, dynamic code analysis tools, cloud-native tools that you are using to make your code functional safety compliant, and so forth. And then in the last session, I'm sharing some best practices, how APTIV is developing a continuous delivery system with real-life examples and some videos from our radar departments. So let's start with the vehicle architecture evolution, or how my colleagues are talking about revolution. Martin is smiling. So as of today, we are coming from hardware-defined vehicles. We are coming from code that's deeply embedded into the ECUs. So in a typical development project, we are spending 80% of the time in integrating code into the hardware. So we are typically very fast writing code, ADAS applications or AD applications, but most of the time is wasted to integrate this code into the final hardware. And then we have to integrate the code also in different types of hardwares and SoCs and overall systems. We are also coming from waterfall-based development methodologies. We are slowly transitioning into agile development methodologies, but I'm still seeing in APTIV a lot of projects who are following a waterfall-based development methodology, but it changes. With a new generation of developers and younger people, it changes. We are also coming from domain software stacks, like fully capsulated ADA stacks running in one domain. Today, we are transitioning into zonal architecture. So we are working in the first zonal architecture-focused OEM projects, and the goal of these zonal architectures was to reduce the physical complexity, so to clean up the zone itself. But we never touched the software so far. The next area that's starting very soon, and you don't see any information about the years, is that we are transitioning into the software-defined vehicle area. So our goal is to fully abstract the software from the hardware, and this is also what APTIV would like to focus on in the COVESA consortium, to talk about a potential vehicle abstraction layer, about a device abstraction layer, to talk about safety-critical container technologies, and also to focus on improving the VSS and this great new project that was presented yesterday by Renesas and BMW around the data-centric architecture in the vehicle. So we are also shifting into new development methodologies. We are describing them as the end-to-end cloud-native DevOps methodologies. And there's an interesting project that I will introduce you to based on the latest acquisition of APTIV. We've completed the acquisition of Wind River. Hey, Brandy. Brandy is also part of the board of directors from Wind River and supporting us there. And we are talking later a bit about the Wind River Studio. The future is clearly in the area of the cloud-native vehicle. There are some pretty interesting use cases in the area of cloud-native vehicles, such as reducing the overall costs of the in-vehicle compute hardware by representing compute devices as thin clients in the vehicle and to off-board compute. We are also seeing or envisioning that the vehicle will become a cloud-native software development environment, something like a Kubernetes on wheels. And this is what we are also envisioning what will happen during a couple of next years. How APTIV sees the future is that we are requiring a full end-to-end lifecycle management. And we are dividing this area into 4 different sub-areas. The first one is described by the so-called development area. So we are requiring cloud-native development platforms to enable an engineer to develop cloud-native applications. We are also requiring a single pane of glass that offers the developer capabilities around deploying functionalities over the air into the vehicle or into an ECU that's located at a different location. This is also a challenge that we are having internally in APTIV, and I'm talking about this a bit later. So I'm referring to remote hardware in the loop testing, for example. The third area is described by operations. We would like to collect data from the vehicle to improve the ADAS algorithm and then to shoot out an update over the air back into the vehicle. And the last area is described by services. So we would like to push out feature updates over the life cycle of the vehicle back into the vehicle. I'm always referring to this cool Tesla use case. Tesla introduced the new stop sign detection and traffic light detection 1 or 2 years ago over the air. And they are using each and every driver that's interesting and contributing data as a beta tester to collect data and to improve the traffic light detection and the stop sign detection. And as of today, 2 years later, if you check out this new stop sign and traffic light detection at tesla.com, you can buy it as a feature. So this is how Tesla develops and enhances functionalities over the different years and continuously. We are also creating a lot of new value for APTIV itself. So APTIV utilizes these new cloud-native development methodologies internally and in collaboration with our customers. So most of our customers and also APTIV is moving into the cloud and utilizing cloud-native tools to develop cloud-native applications. So the cloud brings a clear value for APTIV and our customers itself. Just a small side note, if I'm talking about the cloud, I'm not referring to public cloud, I'm referring to private clouds and also public clouds. So cloud for me is one term to describe cloud-native development methodologies. So what is required to develop software-defined vehicles? How does the ecosystem look like? And we are requiring 4 independent ecosystems. The first one is a machine. A machine is a hardware device with the complete software package installed on this machine. I'm comparing this to my smartphone without applications, without anything, just my smartphone and without any personalization. It's a standardized machine, it's a standardized smartphone, and we are requiring to develop these machines in less than 18 months and not in 2, 3, or 5 years. And this is a typical time that a customer program is running. The third independent ecosystem is represented by devices. A device is, for example, a camera, a radar, a LiDAR, an actuator, a window lifter. It could be everything that we have in the vehicle itself. And as we all know, we are having hundreds of different devices in a vehicle. The third independent pillar is the application. The application is, in our vision, running in a container, in an OCI-compliant container that I'm talking about on the next slide. And the application must be abstracted from the hardware. In the ideal case, the applications is fully hardware abstracted and can be deployed to any target. I'm also comparing this again to the smartphone area, to Androids. You can develop an Android application and you can deploy it to almost any Android smartphone from any manufacturer. And the fourth independent ecosystem is represented by the DevOps platform, the WindRiver Studio that we are talking about a bit later, to enable developers to benefit from cloud-native development methodologies, from cloud-based services, and also to give a single pane of glass to a developer to enable him to develop applications, to deploy applications, to improve the performance of applications, and much more use cases. So we are describing this as the APTIV SVA. SVA is standing for Smart Vehicle Architecture, and I would like to introduce you on one slide into our high-level design. So first of all, we are having the different applications, different sensors and actuators, devices in general. These devices are connected to the PDC. The PDC is representing our zone. And now you see the first red line, the horizontal line that we are describing as the device abstraction layer, because we must abstract the hardware devices and represent them as a software entity in our software architecture. The second cross horizontal line is describing the vehicle abstraction layer. So the PDCs are connected with the central vehicle controller, and the central vehicle controller is abstracted by the vehicle abstraction layer and serves higher level functionalities such as the OSP, our open server platform, to offer ADAS functionalities and level 2 or a level 2 plus autonomous driving system, or also infotainment use cases. And Android is, for example, running on the OSP. And the whole stack is also connected with the cloud to enable over-the-air updates and feature enhancements, and also to share data back with the developers in order to improve some functionalities. So this is our high-level picture of how this smart vehicle architecture looks like. And on the next 4 slides, we are diving a bit in detail into this architecture. So first of all, we've talked about machines. A machine must be standardized. To enable a developer or APTIV or a customer to... Question?
Yes.
Yeah. Yes.
So what about legacy that probably will not be part of business or zone architecture? And so further consider these as a device?
We are considering them as a device, and our vision is also to abstract them as a software functionality in a container. So to up-integrate these legacy ECUs by a software functionality. But I guess we are still a couple of years away. Yeah. Yeah. I have to think a bit. So our vision is to have, for example, a classic AUTOSAR or an adaptive AUTOSAR running in a container, in a ISO 26262 compliant container. This is our vision, and this is, for example, also something that we are working on to up-integrate these old legacy ECUs. In an operating system. Yeah. Can you repeat the question, please? Mm-hmm. Yeah. Yes. Correct, correct. So the zones are becoming more powerful in a couple of next years, and we are also seeing that to have a small SoC instead of a microcontroller in the zones. Martin, would you like to jump in?
Yeah, so also what we do here is we overwrapped, and in some cases we will also connect the legacy ECU, control it via CAN or via LIN, and then translate this proprietary behavior and the proprietary communication down to the standard bus, to the ECU, and translate it into this service-based API on top.
That makes more sense. You're going to keep the ECU as is.
In some ECUs we will keep them, and some
Containerized API to it. That's what you're saying.
that's part of that story too, to say, okay, this is a way in order to translate a legacy world into a service-based world in the zone compute. So that's...
I want to have a discussion on this, but I have another question.
Yeah.
Go or you're-
I guess we are running a bit out of time, and we can have a discussion maybe offline, yeah? Cool, great. Okay, so standardized machines are required to implement this smart vehicle architecture, and as we've talked about already, currently the ECU development is deeply integrated into the hardware and strongly depends also on the hardware. So we are following some open standards, and there's one OCI standard that we are following. It's called the Open Container Initiative, and we are integrating these OCI containers into our operating systems that are coming from Wind River, such as the real-time operating system called VxWorks, and also Wind River Linux, that's able to run containers on the edge with a lightweight container runtime environment. The whole solution is ASIL-D certified, and enables us to run any type of OCI-compliant container in these operating systems. So these machines are required, and they must be standardized. They are consisting of an operating system itself, a board support package running on these operating systems, as well as a middleware, a communication middleware, and a service-oriented architecture running on these devices. Container runtime environment like in Kubernetes running in these machines, and then the OCI container itself. So let me try to give you an example based on a real use case. So we're having the window lifter, for example, connected with the PDC. The window lifter is connected through a LIN bus with the PDC, and also the window lifter switch pad is connected with the PDC. We are now representing this window lifter and the window lifter switch pad as an OCI compliant container in the zone on the PDC to enable some higher level functionalities from the CVC. So the CVC, oh sorry, I have to go back one. So the PDC is abstracted by the so-called device abstraction layer, then to the CVC. And now let's go to the next slide. Here you see the different PDCs I was talking about some seconds ago. These PDCs are abstracted by the device abstraction layer and connected through Ethernet with the CVC. The CVC can now, for example, implement a higher level functionality, such as a use case around you are pushing the button in your vehicle and your windows are going down or your windows are going up. So the CVC implements these higher level functionalities who are also running in a container, abstracted by this device abstraction layer. The CVC itself is then abstracted by the vehicle abstraction layer to higher level functionalities. So let's take now a look to the full picture of our smart vehicle architecture. The CVC is now abstracted by the vehicle abstraction layer to the OSP, and the OSP can now implement higher level functionalities. Let's take a higher level advanced ADAS functionalities, such as, let's assume the autonomous emergency braking system is triggering or your vehicle detected a crash. Then the OSP can send out a signal to the CVC that the doors are getting unlocked or the windows are getting unlocked, and everything is cascaded down to the CVC, and also the PDCs. So our vision is to introduce containers to all layers of automotive compute, from OSP down to the zones. How do we enable this? So we are enabling this, and we are enabling developers to implement these kind of systems throughout an end-to-end DevOps platform. And this is a project I was talking about a bit earlier, the joint project between APTIV and Wind River, and that we are developing a DevOps platform that enables the developer to develop automotive-grade applications, to test automotive-grade applications out of a single pane of glass. What you can see on the picture on the left side, there's a pipeline manager that I can use to connect different tools with each other. But we are also enabling the developer to deploy functionalities over the air, or to virtually test functionalities on a virtual target, and I'm talking about this on the next slide, or to focus on the so-called operate area in collecting data from a fleet of vehicles, letting the data flow back into the platform to improve some ADAS functionalities, to validate these ADAS functionalities, and then to shoot out an update back into the vehicle. So we are describing this as our APTIV next-gen software architecture and tools. And in the develop area, we are having a product that we call the Wind River Studio Gallery. And the Wind River Studio Gallery is an automotive-grade marketplace in that APTIV partners can offer tools to engineers, and also APTIV can offer proprietary homegrown tools to their own engineers. We are having in APTIV more than 200 different homegrown and proprietary tools that we are using. And we would like to offer a selection of these tools throughout an automotive-grade marketplace to our engineers. Tools like unit testing tools, dynamic code analysis tools. So we are actively talking with the typical tool providers that you know around unit testing and AUTOSAR code generation to integrate these tools into this automotive-grade marketplace. And you can check out a web browser and type in gallery.windriver.com, and you will see our first generation of the automotive marketplace, and that you can install tools into this DevOps platform. It is very similar to Atlassian's marketplace that you may know. We are also having a tool called the Pipeline Manager that enables the developer to connect different tools with each other to get an end-to-end workflow in place, from getting code out of the code repository to the unit testing of these tools, of the code, or dynamic code analysis or vulnerability analysis. We are also having a so-called test automation framework to focus on the reusability of tests, because we've identified internally that we are wasting a lot of time in not reusing tests from one program to another program, or in not reusing tests from one project team to another project team. So the so-called test automation framework helps us to manage tests and to execute tests. And what I personally like very much is the so-called virtual lab, and that you are enabling engineers to reserve virtual or physical instances of SoCs and ECUs. So we are starting to virtualize microcontrollers. We are starting to virtualize SoCs. One of the first SoCs that we are supporting is the S32G, for example, but also some microcontrollers from STM. And you can use these SoCs up to ECUs then in a virtual lab to test and validate your software pieces. In the deploy area, and I'm spending a lot of time on this slide, in the deploy area we have products that are focused on the in-vehicle topic, so the VxWorks, the real-time and safety critical, container-enabled operating system, a virtualization platform, a Linux based on the Yocto project, but also the container orchestration that I was talking about earlier that enables you to orchestrate containers from from the cloud into the vehicle, or to orchestrate containers in a distributed environment, such as the smart vehicle architecture. APTIV is developing a so-called communication middleware, as well as a service-oriented architecture. I'm having two colleagues here sitting in the audience, our architects for these two products, and also we are partnering with some companies around the software-defined networking. The operate area is everything about digital feedback loop. How do we get data from a fleet of vehicles back into the platform to enable a developer to reuse data and improve functionalities? So the benefits of an end-to-end DevOps platform that's seamlessly connected with a software-defined vehicle is clearly about getting a continuous delivery approach. So each action informs the next action in an ongoing cycle, as we can see right now also on the screen. And very often you're having multiple teams and even suppliers and also our customers are starting to work with us in a co-sharing model on the same repository to develop new products. You need an end-to-end DevOps platform to enable this continuous delivery approach. As we've talked about, continuously integrating applications, continuously testing applications, and continuously deploying applications. The best practice that I'm happy to share is, and I guess most of you are aware about this, is to integrate code early and very often, and also to focus on a fail-fast mentality, and to get this end-to-end DevOps tool chain as quickly in place as possible. To develop, deploy, test, validate, deploy on virtual targets, to derive some metrics out of these tests and to fix some bugs and test again. That's it from my side. I'm having much more slides, to be honest, but we don't have enough time. But this presentation will be available at the COVESA wiki. You can download this presentation from there. There are some more slides coming around sharing best practices, and I'm quickly going through it without talking in detail, how we are continuously developing throughout the three different phases, pre-production, early production, and after production use cases. There's also a use case around continuous integration, and this is a great white paper. To that, I was adding the QR code at the end of this presentation, how we are how we've implemented a rapid build technology using Bazel as the underlying build system to speed up the build process. Because we've identified that sometimes a build process takes us 8 to 10 hours. We are able to parallelize the build process. It's also talking about continuous testing, how we are collecting real data and how we are transforming real data, utilizing machine learning techniques into simulated data to create permutations of the data. Rule of thumb, we are driving in between 400,000 to 1 million miles of data per customer project across the world. That's a lot, so we have petabytes of data located in APTIV data centers. Use cases around continuous deployment, continuous monitoring. There's one video that's also available at LinkedIn. And I like this video because everything what you can see here on the right side, it's a live stream, was created using a radar. And we are able to detect vulnerable road users and vehicles only using the radar instead of a camera. So the two camera images on the left side are only illustrative. And it also shows a data set that you can download from Motional, the new scenes data set. It's a fully labeled data set, 360-degree scenes, that's publicly available. Continuous feedback, and this was my summary slide around the unified development environment. But I'm coming to an end to answer some more questions. And last but not least, there are two great white papers that I encourage you to read. Best practices about CI/CD, and a new white paper around best practices in standardization. COVESA is mentioned there also, but also Steve, also working groups like SOFI and STV.OS by the Eclipse Foundation, and also some other working groups. So check them out. As mentioned earlier, the presentation is available online after this talk, and I guess we have time for one question. One question. You mean, so if we are starting to virtualize SoCs and ECUs, we are much faster in developing automotive applications. So faster go to market. I guess also we can improve the quality massively because we can test early and often utilizing virtual SoCs. And one of the challenges that we are having internally in APTIV, especially in the early stage of a project, is that we don't have any hardware. So very often the hardware is not available internally, or the developer is not having physical access to the hardware because the developer is located in Germany or in Poland, but the hardware is located on the East Coast. So you can remote deploy your functionalities and test these functionalities. And especially in times when the SoC is not yet ready, you can start developing, start testing and deploying without having the SoC available from NXP because we're having the virtual model. So it's time saving and cost saving, I would say.
Thank you so much, Florian.
Yes.
Thank you so much. And Florian, a round of applause for his very enlightening talk. So we are transitioning now into a panel, and this is going to be complicated. We've got two panelists who are local and two panelists that are remote. We need to set up a couple of chairs. So those of you who are standing in the back, come on, there's plenty of room up front. Come on up and we'll get you all settled, and give us just a couple of minutes to set a couple of chairs, and then we'll go from there.